So maybe we should restart. So the second speaker of this afternoon is Gainutdinov from Tours, and the title is on the semi-simple Verlinde formula.
Thank you. I would like first of all to thank organizers for the invitation and giving me a possibility to talk here. My talk will be on the non-semi-simple Verlinde formula. So this is will be about my work with Ingo Runkel. Back to 2017, we proposed sort of version of Verlinde formula for CFTs where representation theory of VOAs are not semi-simple, so-called logarithmic CFTs. And also I want to talk more recent results with our previous student Johannes Berger and Ingo Runkel also. Let me begin with sort of overview with classical aspects of Verlinde formula. For me, Verlinde formula is like, okay, there are several definitions. What's Verlinde formula? It's sort of genus zero. I will be mostly talking about genus zero case. So it's the Verlinde formula that relates fusion rules of, say, irreducible representations of a vertex operator algebra to modular S transformation of the corresponding characters, right? And in these cases, we should distinguish two cases. One is a sort of semi-simple situation, or so-called rational CFTs, or strongly rational VOAs, where representation categories are semi-simple. And this case is well understood. It goes back to Verlinde, to 1988, and then it was proven in a big generality for strong rational VOAs by Huang in 2004. I will talk about it more. And the case I'm interested in, as I say, is log-log CFTs, or non-semi-simple setting. Many people also worked on that. I didn't give a list of names, different approaches, but from my point of view, there is still not so well understood the general picture comparing to what we know on rational CFTs. And I will try to give, I'll propose a version of this non-semi-simple Verlinde formula, sort of, which is for a general picture for certain class of VOAs, C2-confined VOAs. And because station is non-semi-simple, the algebra part is much more complicated. Actually, in semi-simple case, the algebra or associative algebra behind the theory are quite simple. They are semi-simple, actually. Here, the algebra can be quite intricate. So the appropriate language will be a categorical language. And I will use certain categorical algebra and certain theory of traces on tensor categories called modified traces, which were recently attracted by also in quantum topology. People like them. I will also use the notion of pseudo-trace functions introduced by Miyamoto, Ariki, and Nagatamo, and we will mix all these to derive a certain version of this logarithmic Verlinde formula. Okay, let me begin with the Verlinde. So Verlinde conjectured these fusion rules that if you use irreducible representation UV and you get multiplicity of W, and this multiplicity can be expressed in terms of matrix elements of modular S transformation of VOA characters, right? This is a celebrated Verlinde formula. And in general setting, interesting for us, so V will be a rational C2-confined VOA, non-negatively graded, simple self-dual. And Huang Lipovsky, back to 1905, they proved that a repo V of certain class of representations, also non-negatively graded, is a braided fusion category. So first of all, it's semi-simple, and there is a braiding, and it's monoidal category. So the tensor product of two simples we can decompose into irreducibles, and this NUVW expresses the multiplicity space. But to prove this formula in this general setting, it took basically 16 years. It's only in 2004 it was proven. But to give a precise statement, let me introduce VOA characters. So let M be a representation of my VOA, and what I call by character is a certain function which is linear in elements in VOA and analytic in tau in upper half plane. And I define them as I should introduce them. So it's trace function on this module M, where you have a standard thing which is very familiar to every you, e2 pi tau 0 minus u 24. But actually, we need extra thing. We need a so-called zero mode of a given vector, right? So it has input vectors and tau. And I have to calculate trace of this operator. Okay, and Zhu in 96 have proven that such a map is analytic in tau. And also very important, that's why basically we need this ingredient V, that they are linearly independent as functions from V cross H to C. Also to talk about modular S transformation, I need a special grading. So we have a grading by L0, but to talk about Zhu's results, we need a special grading that Zhu uses, so-called exponential grading. So it's just different grading which basically corresponds to conformal transformation from Z to exponent of Z minus 1. So it's conformal transformation from torus to amorous, basically. Okay, so and this is grading with respect to some operator which is like L0 minus 1/2 L1 plus 1/6 L2 and so on, so on. We call it exponential grading. And for a homogeneous element from this now, with respect to this grading, Zhu have proved that a modular S transformation, so when we replace tau by -1 over tau with appropriate power of tau to the conformal dimension, I mean not conformal dimension, to this grading H, that it can be again re-expressed in terms of characters over irreducible representations with some elements SMX. So that's a theorem in this generality. So using these S matrix elements, the Verlinde formula in this generality in rational case was proven by Huang 2004. And it's important to separate three parts of this problem of proving this statement. The first part, which is a very hard problem, and proven by Huang, is that representation of this strongly rational VOA is a modular fusion category. Modular fusion category in the sense of Torai, right? So it's a ribbon category. So the most non-trivial part to prove that there is a rigid structure. So as I said, it's a braided fusion category, but also with rigidity, which means that every object has dual. Moreover, braiding is non-degenerate. I will talk about it later, but basically it means that the matrix coming from the Hopf-link, or using double braiding, right? So actually, you also use right. So basically, this is my matrix elements. C is a braiding, so I braid my irreducible U and V 2 times, and then I take a trace. So which means just I close the thing. This is categorical trace, right? So this gives me a morphism in category from 1 to 1, so it gives me a number. So this is SUV. And we run over classes of isoclass of irreducibles, so this gives me a matrix. So the matrix is just a bunch of these. And in modular fusion category, this matrix has to be non-degenerate, right? So this is the definition of modular fusion category in sense of Torai. And why I have proven that Rep V is a modular fusion category, this is the first thing. Then the structure constants NUVW you can express using Torai's module. Okay, how to say? So we have S transformation of the characters which come from BUA, but also we have S transformation that comes from the date of modular fusion category. This was introduced by Torai back to '94. And this is a definition. So basically, this is a definition of the S transformation. Or the S matrix. So you just compute trace, categorical trace of the double braiding. And then it's actually quite easy proof. So with this S transformation, it's not hard to prove this formula for NUVW, which look like this one, but here you use categorical action, right? Which has seemingly has nothing to do with VOA. And then the last step, which is also hard, which was proven by Huang, that for C or FV, that VOA S matrix just agrees with categorical S matrix. This is extremely deep and non-trivial result, right? So using these 3 points, this is the proof. of this Verlinde formula. So it took, 16 years to prove it. Okay, now in non-semisimple situation, of course we have problems. First of all, tensor product of simples is not necessarily decomposed onto simples. So typically you would have some other objects which will be indecomposable but reducible. So it's not immediately clear what we should call by fusion rules. Another thing that you can still also define categorical S matrix by this formal expression using the same categorical trace, but it's degenerate. In non-semisimple situation, this is always degenerate matrix. So it also doesn't make sense to use it even formally, as in previous formula. Also on the OA side, there are problems that model transformation of characters is generally not a sum of characters. It's a sum. There are some more complicated modular forms that appear. Okay, let me first explain the. Okay, we're going to, of course, to solve all these problems. What I will call by NUVW, because in non-semisimple station there are several choices what you could call NUVW. But what will NUVW will be for me? It's a structure constants in the Gainutdinov ring, right? So as I say, the tensor product of two simples, it will be decomposed into simples, but plus some indecomposable reducibles. And instead of calculating multiplicities of direct summands, I will calculate multiplicities modular relation in Gainutdinov ring. So if you, just let me remind you that every object in the category has its Gainutdinov class. So what it is? It's a free Z module with a basis given by reducibles. So what do you do with indecomposable but reducible objects? Let's say if you have an exact non-split exact extension of some object, say C, and it's extension of A and B, right? So it's not direct sum of A and B, but it's just some non-trivial non-split extension. In Gainutdinov class, you just take A plus B, and so on. So every object can be written as some linear combination of these classes of irreducibles, right? And it has multiplication coming from the tensor product structure. So basically, if you want now multiplicities, they tell me how many irreducibles W are present in subquotient structure or in Jordan-Holder series as sections. Okay, so this I will call fusion rules. And to write the sort of Verlinde formula, I will follow the following steps. The derives, remember that was important part of the categorical L2Z action. This action will be replaced by what was introduced Lyubashenko. So Lyubashenko generalized Derives' notion of modular fusion category to the notion of modular tensor category, which is not necessarily semi-simple. And he already gave us a good notion of categorical L2Z action. I will talk about it a bit later. Anyway, because of Lyubashenko, we have such a categorical S matrix in non-semi-simple setting. And it's relatively easy to express these structure constants in terms of this modular categorical S action. Then on the OA side, I will use, we have action, SL2Z action, or just S transformation on the space of pseudo trace functions. These are generalization of characters, and they involve so-called Hattori-Stalling traces. I will talk about them later, and then I will give a precise relation between these two categorical Lyubashenko's action and the OA action of pseudo characters of pseudo trace functions. I will give precise link between these two spaces, and using this precise link and using expression NUVW in terms of categorical S action, we can express, therefore, NUVW in terms of VOA as action. Okay, let me start with the modular tensor categories.
On the previous slide, that's step 2. Is this some general categorical construction, or?
Yeah. Step 2 is general categorical construction. Yes. Okay. Yeah. I will show you. Yeah.
Okay. Thanks.
Yeah. So I start with step 1, with the Lyubashenko's construction. So by Lubashenko, okay, the definition of Lubashenko, what we should call modular tensor category was different than what I give here. But what I give here is equivalent to initial Lubashenko's definition. And this was proven by Shimizu 2015, so relatively recent. And so this is cheapest definition of modular tensor category. So it will be a Riemann category, plus I ask finiteness condition. So for me, it will be finiteness means that as a category, it's equivalent to just as linear category. It's equivalent to a representation category of some finite dimensional associative algebra. Okay? So what it means? It means that in my category, I have finitely many isoclasses of simples. I have projective covers for every simple, so I have enough projectives. And I have finite lengths. Every object has a finite length. Okay? But it might be non-semisimple. Plus, so it has to be Riemann category plus factorizable conditions. So what factorizable, to introduce factorizable, I mean, I need to say what is transparent. So I call object transparent if with every other object, double braiding equals identity operator. So you can sort of, so it's transparent in terms of braiding to every other object. And we call the categories factorizable if the braiding is non-degenerate in the sense that if X is transparent, then it necessarily direct sum of tensor units. So in factorizable category, we have only trivial transparent objects. So that's conditional on non-degeneracy of the braiding or factorizable. If C is additionally semi-simple, so here it's not supposed to be semi-simple, but if it's semi-simple, then this notion of modularity is the same as Touraev's in terms of this S matrix that I draw. There are many examples of modular tensor categories. From a computation theory point of view, the famous one are so-called small quantum groups, the odd order of root of unity. So they produce examples of such modular tensor categories. Okay, in 1994, Lubashenko introduced this notion of modular tensor categories, but also for him it was a sort of gadget that produced you a family of mapping class group representations. For every model tensor category, Lubashenko explains us how to construct representations of surface mapping class groups. And they are represented on home spaces in your category C. So let me give an example of surface of genus G without punctures, so just undecorated surface of genus G, and mapping class group of this surface acts on this home space. So you take a certain special object, I call it coend. So it's a coend of certain functor which send a pair xy to x star y. And you calculate the space of basically coinvariance, right, of G's tensor power of this object L. So this object L is a central object in all this construction. It's a certain universal object which can be written as a coend. It's meaning that it's universal to every dinatural transformation to any object A. I prefer to skip explaining what it means because of lack of time, but it's certainly universal object, and moreover, if category is braided, and this is our case, it has a Hopf algebra structure in the category. So in every model tensor category, we know that it exists, and actually we have a full control on this object. So we know that in every model tensor category, I have such a canonical sort of or universal Hopf algebra object. Another way to think about this Hopf algebra object, is that a category of modules of this Hopf algebra internal to C is equivalent to Drinfeld center of C. Okay, so it's such a nice object. As equivalent as braided tensor categories. Because it's Hopf algebra, L mod is also a tensor category, moreover it's braided, and right, okay. Right, so these mapping class group representations, in particular SL to Z action, so I needed all this just for S transformation, but I want to give you a more global picture that for every surface, we have mapping class group representations on these home spaces from the special object tensor G to 1. And I don't give you definition because it's quite technical, but Lubashenko uses Hopf algebra datum of this object L together with universality property of L to define in terms of generators, how generators mapping class group act on these Om spaces. Okay, and this action generalizes to Rives construction in semi-simple case. In semi-simple case, this coend is very simple. It's just direct sum over class of irreducibles U star tensor U. Very simple. And in J1 case, we therefore have, so the space where SL to Z act, in the torus case, it's home from L to 1. And in a finite tensor category, it's always equivalent. There is canonical isomorphism with endomorphism of identity functor. So it's a space of natural and the transformations of identity functor. And we have explicit expression of this categorical S action on such a space. So that, for example, force power of S is identity. Of course, there is SL to Z action on this space, but for the most of the talk, I need mostly S action. Let me give, and this is all under control. Let me give an example in case of K.Hep algebra. We know that sources of model tensor categories, they are coming from, for example, from K.Hep algebras, factorizable ribbon K.Hep algebras. So let's assume H is factorizable ribbon K.Hep algebra, and then there's SL to Z action. So what will be home L to 1? As I said, it's endomorphism space, it's end transformation of the identity functor. In this case, it's just the center of H. So it's very simple. So this space where SL to Z acts, it's just the center of this algebra H. And S transformation acts in a very compact, there is a very compact expression. So you take a central element and you map it to this expression. What is this expression? Okay, I have to use this K.Hep algebra datum. As I said, as I assumed, H was ribbon. So in particular, it has a universal R matrix. And then you compute monodromy matrix, like R21R, okay? And then you use integral. So K.Hep algebra, fine dimensional K.Hep algebra, necessarily has a special linear form, which is called integral. It's unique up to a constant. So it's also sort of canonical element up to normalization. Anyway, you take such canonical form, right integral. You eat your element Z with the first leg of monodromy matrix, and then you do nothing with the second leg, right? So it will be some complicated combination in terms of H algebra elements. And you get central element, new central element. So this is how S transformation acts. Okay, this is under control. And now the next step is to express fusion rules in terms of this Lubashenko S action. For this, I need to introduce internal characters. They will play the role of VOA characters, but they have categorical meaning. And to introduce that, I need, of course, the structure. I hide in previous slides. I hid the fact that coend, it's coming naturally with the canonical family of the natural transformations. So it's equipped actually. So when I say it's coend of that functor, it's not just an object, but it comes with a family of canonical dimensional transformations. Okay, so this is a part of the this object and this family of maps, and they should be dinatural from X star X to L for every object in XCC. So this is part of data of the coin, and this is also under control. And Fuchs and Schwager in 2010, they introduced a well-defined map. They proved a well-defined map from Grothendieck ring. So this is my structure constants. I'm interested in Grothendieck ring into home 1 to L. So to every class, we associate a map from 1 to L. We use for that first co-evaluation. The category is rigid, so I have such a thing, U star U. And then I use my canonical natural map, iota U, into L. So this is a map from 1 to L. And Shimizu in 2015 has proven that for every U in irreducible, if I run over irreducible classes, all these chi U as linear maps, as morphisms from 1 to L, they're linearly independent in this space. I need one more step. So we have these internal characters in home 1 to L. In every unimodular category C, in particular modular tensor category C, I have a canonical isomorphism between home 1n L and home L to 1. This involves also K.Hep algebra data of L, so I skip this part. But there is a certain canonical iso that uses integral of the coend L. And this ISO is also canonical. This ISO is true in every finite tensor category. You don't even need braiding or whatever. Anyway, so I skip the definitions because it's quite technical, but they are canonical ISOs. So for every such internal character, I construct element phi u, which is endomorphism of identity functor. So you should think about this as a certain central element. If your category is realized by a Hopf algebra, it's a certain central element. Okay? So they're special elements, and they play a special role. They will be analog of usual characters of UA. So what we have so far, I will give you explanation of what is phi u. I didn't describe these maps, but maybe let me give you a picture. So this is a string diagram for phi u. So we know it quite explicitly. As I said, it's endomorphism of identity functor, and on components, it behaves like that. It's endomorphism of X. You see there is coevaluation, evaluation maps. There is this iota, the structural maps of the coend, and there is this special co-integral of coend. So we have explicit expression, and the property of this phi u, another maybe way to think about it, is that modular S transformation of phi u, it provides you this very simple picture. So Lubashenko's modular S transformation, it sends phi u to another endomorphism of identity functor, which on components just acts via open Hopf link. So basically you use just double braiding and evaluation coevaluation. Okay? And this phi u, they are really analogs. You know them very well in semi-simple situation. When C is semi-simple, these phi u's, they are just idempotents corresponding to a given u. So they act on every simple object V by 0 unless V is ISO to u. In non-semi-simple situation, they are very far from being idempotents. They are sort of the maximal, the maximal radical element. So first of all, that phi u acts on projective cover of u by a non-zero endomorphism. It acts via zero endomorphism for every projective cover, which is projective cover of irreducible that is not ISO to V. So it's like delta function. It just acts non-zero only on its own projective cover, corresponding to u. And on its own projective cover, it acts, it sends the head to the socle. So it's the most radical element, head to the socle. Okay, so these are these elements. And another important property is that, as I said, these open Hopf links, we have a map, we have isomorphism of algebras. That's important statement that this map from Grothendieck ring to endomorphism of identity functor via S transformation of these phi u elements is a ring homomorphism. And this ring homomorphism is isomorphism if and only if C is semi-simple. So in our setting, it will be just an embedding. Okay, I introduced this necessary ingredient, and let me give a categorical non-semi-simple Verlinde formula, which is sort of analog of Turayev's. It's a bit more intricate, but anyway. So let C be factorizable pivotal finite tensor category. So this is in theorem with Ingo back 2016. We gave it in a more general setting, just a factorizable pivotal categories, but MTC is okay. So the structure constants in Grothendieck ring can be uniquely recovered. So first of all, we should know the algebra and the morphism identity functor. Okay. Then we identify these elements, phi u, the special elements in this algebra. It's a finite dimensional commutative algebra. The linear map SC, this Lubashenko's categorical S transformation. I mean, this is what we also have. And we have the following statement that multiplication of images of these internal characters by S transformation and then applying inverse of S transformation is necessarily decomposed again on these internal characters with structure constants NUVW. Or saying differently, let me introduce a pairing on this span of phi's or on the span of internal characters inside my endomorphism ring of identity functor. I introduce the pairing phi u, phi v, delta uv. And then NUVW can be computed via this pairing. Like phi w, we have to pair with this element. And it uses only categorical action S, and it uses these internal characters. And one can show that in semi-simple case, this formula reproduces this Turaev's formula. Okay, so this is what I will call non-semi-simple Verlinde, categorical Verlinde formula. Now let's go to the VOA side. For me, the setting will be. Yeah.
Assume finite number of simple.
Yeah, that's what I say. For me, model tensor category was finite. I said I mentioned finite as condition.
Okay.
That because otherwise cohen does not exist in the category. Because I use as cohen, but it's some object, but I need that it belongs to the category. Right. And in particular, this finite condition will be satisfied by C2 cofinite case. Okay. So VOA is equal to cofinite, non-negatively graded with okay. The zero component is just one-dimensional, and it's simple as VOA module and self-contragradient. And for representation category of this VOA, I will look at the V modules, which are can be decomposed into direct sums of generalized eigenspaces of L0. This is where a logarithmic situation comes in. So L0 allows to have Jordan blocks, non-trivial Jordan blocks. They should be bounded below and find composition theories. And then in 2010, Huang, Lipovsky, and Zhang, they proved that such rep V in this setting is a finite linear category. This is finite condition I just mentioned, that it's equivalent to, as a linear category, it's equivalent to representation category of some algebra, finite dimensional associative algebra. And it also has a braid monoidal structure with simple tensor unit. Okay, and the conjecture, or yeah, I will work within this conjecture that for this class of rep V, I just defined self-contragradient, C2 cofinite, that rep V is modular tensor category. Of course, not necessarily semi-simple. And of course, it might work only in self-contragradient case, because if V is simple, so if we drop simple and self-contragradient, we know examples of C2 cofinite VUAs where this is not true. Okay, so I assume that rep V is modular tensor category. And I will need again back to work Zhu 96. He introduced the space of torus one-point functions. So it's a certain subspace in functions, linear in V, analytical in tau, in H, and they satisfy certain differential equations. So I skip this part, but Zhu gives a definition what we should call torus one-point functions. So there are certain solutions of differential equations plus these conditions. And in that setting of C2 cofinite VUAs, Zhu has proved that this space of torus one-point function is finite dimensional and closed under the action of SL to Z. And examples of such elements in C1V are characters. Characters are just, as I discussed, it's trace with its zero mode and so on. So what we have from Zhu is that we have VOA S transformation. I will denote by SV. So you take this torus one-point function, and it's sent to tau minus to the h. Again, V is in this exponential grading. So this is my S transformation, right? And we know that SV acts on this C1V. So the idea is that now we are going to link C1V with this algebra of endomorphism of identity functor for rep V. And we are going to relate the corresponding S transformations on the OA side via this, and the categorical S transformation via Lubashenko construction. Okay? And very important step at this point, I will use parametrization of elements from C1 of V, of torus one-point functions, by symmetric forms on a finite dimensional algebra. So for this, I have to understand projective objects in rep V. I have to understand projective covers. So I take projective generator. Projective generator is like maximal, but basically take direct sum of all projective covers, of all simples, right? This is a projective generator. This is an example of projective generator. And take endomorphism algebra of this projective generator. So if you want intertwining operators from G to G. Or if you want the centralizer of your VOA V on this particular representation G. And it's a finite dimensional algebra. Also, its category of representation is equivalent to rep V, just by construction. So rep V has the same representation category as E mod. But at this point, E is just associative algebra. And now expand this projective generator onto generalized eigenspaces. it's clear that one can prove that at every h degree, here h is just normal L0 space, right? So this is just normal conformal grading. GH is a projective E module. Now I'm going to study symmetric forms on this, for this algebra E, or centralizer of VOA. So by symmetric forms, I mean linear forms on E such that phi of AB equal phi BA. Okay? And now I'm going to define pseudo-trace functions. This is definition due to Arika Nagatomo, 2011. So for me, pseudo-trace function, so they're parameterized by these symmetric forms. So what do? I take this sum over my conformal grades and evaluate certain trace. This is called Hattori-Stalling trace. It's not usual trace. Evaluate Hattori-Stalling trace, which is associated to such a symmetric form phi on GH subspace of this particular operator. Let me say a few words about Hattori-Stalling traces. So the Hattori-Stalling traces for any associative algebra, they are linear maps. So it's a given trace, it's a family of maps from endomorphism space of projective objects to complex numbers, right? And such traces are in bijection with symmetric forms. So I don't give a full definition, but I will give you an idea. So they are cyclic, so they are usual traces, and they satisfy also additional condition of right partial trace, which I skip. And on VOA side, right, I have this, of course, the most obvious symmetric forms, which are just trace functions over my representation of VOA M, right? So they are symmetric forms on the algebra E. And they define special pseudo-trace functions, which are just normal characters. So usual trace functions on algebra E, they define usual characters. But we have much more. In non-semisimple situation, we have much more symmetric forms. And in general, Hattori-Stalling traces, they detect off-diagonal part of endomorphism from endomorphism of projective objects. So that's why they're important, because the characters, they only detect diagonal part, sort of, but to detect off-diagonal part of the action, we need Hattori-Stalling traces. And at least in certain situations, they can be explicitly computed, but the point for me is that torus one-point functions we can parameterize by these symmetric forms, via this Hattori-Stalling trace construction. The problem how to link now. So on VOA side, we have these torus one-point functions, and I have VOA action, modular S transformation, and I use parameterization of my torus one-point function in terms of symmetric forms. So I assume I have this isomorphism. So from VOA side, that means that what I get S transformation on symmetric forms of my endomorphism algebra of this projective generator G, right? Now, on the categorical side, I have endomorphism of identity functor of C, which is repo V, and how to link these two spaces. Or the first question, how to get at least one element from these symmetric forms on the algebra E. The obvious one, the categorical trace, right? The categorical trace for C rep V, it's obvious choice because it gives you actually a symmetric form. But the problem that if C is non-semisimple, you can prove that categorical trace of every endomorphism of every projective object is 0. So which means that if our VOA is non-semisimple, has a non-semisimple representation category, categorical trace is just useless because categorical trace of every endomorphism of projective generator is 0. And solution to that is to use so-called modified trace. It's a generalization of categorical trace to non-semisimple pivotal categories. It was introduced in the context of quantum topology by these people, Gir, Kujava, Petireau, 2010, which goes back actually to the work of Turaev, Gir and Petireau, 2009. They introduced a notion of modified dimension. Then they gave a nice concept of modified trace. So it's a good generalization of categorical trace to non-semisimple world. But it will be defined not on the full category, it will be defined only on projective objects or only on the endomorphism of projective objects. So I will be dealing now with a full subcategory of projective objects. And what is modified trace? It's a linear form, it's a family of linear maps from endomorphism ring of P to C, this should satisfy two conditions, cyclicity, like to be a trace, but also they satisfy the condition of the right partial trace condition. So they should be consistent with closing components. Okay, the point is that such a trace is unique. So back to 2017 with Ingo, we proved that every model tensor category has a unique non-zero modified trace on this projective ideal. And the important thing that it's non-degenerate. And non-degenerate means that the algebra E has a structure of symmetric Frobenius algebra. Okay, I will skip this point. Now we are able to link, I'm going to link these two spaces using this modified trace. So because, as I said, it's non-degenerate, I can construct an isomorphism from, so I take my natural and the transformation eta, and I map it to a symmetric form on this algebra. I take modified trace on the projective generator, and I insert G component of my eta, which is in the morphism of G, right? And here I can insert, this is argument. This is argument from this algebra. And this is just some normalization constant, you can ignore it. So basically what we have, so TG already provides a non-degenerate symmetric form. And what we do, we just shift its argument by components of my endotransformation of identity function. And what is important about this map is that it sends these phi m, my internal characters, to just normal traces over corresponding irreducible representations. And an important statement that the pseudo-trace function corresponding to the symmetric form to the internal character, you see this delta G of phi m, is just normal character. Okay, right. So this is just a recap of categorical Verlinde formula we have. So we know how to calculate NUVW in terms of categorical S transformation. We have all the necessary ingredients to make the main conjecture. So on category side, we have Lubashenko's S transformation. On the OA side, we have this SV action on space of pseudo-trace functions or on symmetric forms of the corresponding centralizer of OA. And we have this ISO that links categorical world to these torus one-point functions via this modified trace construction. And the conjecture we have, which we tested in many examples, but it's a far conjecture, about relations between these two S transformations. That the following diagram commutes. So here is a categorical S transformation. Here is a Jou's S transformation on VOA on pseudo-trace functions, and this is delta G I defined via the modified trace construction. The conjecture that this diagram commutes. Let me give you outline, sort of, or practical steps. How to calculate then fusion rules just using VOA data if the conjecture holds. So if the conjecture holds, right, because modified trace is a complicated thing, but actually the VOA meaning of the modified trace is very simple. So you should take a vacuum character and compute modular S transformation. You get some pseudo-trace function which is parameterized by some symmetric form delta, right? So you're supposed to calculate this. So the Hattori-Stalling trace for certain delta of this operator. It can be written. So we identify the corresponding symmetric form. And the claim actually that this symmetric form is exactly the symmetric form coming from modified trace. So it's just a transformation of the vacuum character. So from this calculation, we get a symmetric form, not degenerate. This allows me to define this isomorphism I discussed in previous slide. And now use this isomorphism to transport multiplication from the center of my endomorphism algebra to the space of symmetric forms. The space of symmetric forms, they normally have no natural multiplication. But via this special isomorphism, I can transport it. I denote it via this symbol, this bullet. So on symmetric forms alpha and beta, I have now a special multiplication, which is given by this formula. And now, take your characters, character A, character B, calculate VOA S transformation, Joule's S transformation. You get the corresponding, at this point you should calculate corresponding symmetric forms. Multiply them via this multiplication. Apply inverse S transformation. It should necessarily be decomposed on two irreducible characters. And you get the structure constants. So from this point of view, you use only VOA data. But also, of course, you need to understand projective objects, because you need to understand projective generator. Okay, let me say, I have not much time, but there are many examples when we can, of log CFTs, when we can test this conjecture. First of all, it's symplectic fermions. It's a C2 confined VOA corresponding to symplectic fermions with central charge minus 2n or triplet W algebra in 1P LCFT models. These examples, they can be, the categories can be realized via some quasi-quantum groups. This was also work of many people, or it's a recent understanding of the theories that their representation categories as braid tensor categories can be realized via some factorizable Riemann quasi-Hopf algebras. And in this case, all these necessary ingredients like modified trace, coend, algebra E, internal characters, Lubashenko's transformation, they can be calculated explicitly because it's more like in Hopf algebra world. That's easy. And so one can on the other side do calculations with pseudo trace functions. At least in the case of symplectic fermions, this is what we did with Ingo a few years ago. And with our student Van der Farsad, we tested that conjecture. That conjecture works in case of symplectic fermions for every n. Okay, let me finish with some VOA results if this conjecture holds. First of all, VOAV should necessarily have a simple projective module. So this is due to my theorem with Ingo that every model tensor category contains at least one simple projective object. Another thing is that if model transformation of the character is not a sum of characters, then your VOA module M is not a projective V module. So model S transformation allows you then to detect if module is projective or not. This is due to also my theorem with Ingo that categorical S action maps space of projective characters to itself. So the usual characters, they are not closed under S transformation, but the characters of projective objects, they are closed. And also the characters span space of torus one-point function if and only if V is rational. This is due to theorem of Shimizu. Okay, that was the formula for NUVW. There is, I will probably finish with another Verlinde formula, but for other structure constants, which can be made more explicit. This is a structure constants for K0 or rep V. So notice that in semi-simple case, K0 and Grothendieck ring, they are the same notions. In our case, they are not the same because K0 contains structure constants for tensor product decomposition of projectives into projectives. So two projective covers of U and W can be decomposed into projective covers Px with multiplicity MUWX. And if that conjecture holds, so let me say it this way. Right, if the conjecture holds, then we have the following Verlinde formula for these multiplicities of projectives. You see this MUWX, okay, modulo this B, I will explain it. It has the same structure as classical Verlinde formula. But here S projective is matrix elements of modular S transformation of projective characters. C is just charge conjugation matrix for projective modules. The only difference is that there is matrix B, and it measures the kernel of the map from K0 to Grothendieck ring. And it's determined by the Cartan matrix of C. So if you know structure of projective covers, you know Cartan matrix of category C, you can determine B. And index Y, it runs over basis elements in the image of K0 in Grothendieck ring. Okay? So B is actually not invertible. So in general, you cannot extract MUWX, but it gives you some information about MUWX. It should satisfy this equation, which is indeed like Verlinde equation. And in many examples, like in symplectic fermions, it's actually, it's enough, this equation is enough to calculate MUWX. And so this is how closest we can get to the classical Verlinde formula. In a sense, projective covers, they are analogs of irreducibles. Yeah, maybe I will probably, do I have a couple of more minutes or I have to stop? I can stop because there's another, huh? Okay. I just need a couple of minutes. Okay, that was about this non-semisimple variant of Verlinde formulas. And of course, we used this SL2Z action, or more generally, one should think about mapping class group representations, probably to think about higher genus space conformal blocks. And there is an actual question, can we extend these categorical mapping class group representations of Lubashenko to a proper three-dimensional TQFT, which would produce them? Because if we have such a 3D TQFT, we can also calculate Verlinde formula using topological methods. And this is indeed true. 2 years ago, we proved this theorem with Marco Dorenzi, myself, Gir, Petiroa, Miran, and Ingo Runkel. We proved that every C-model tensor category over every algebraically closed field K provides a 2 + 1 TQFT or a monoidal functor from category of three two cobordisms to vector spaces. There is one technicality that cobordisms should be admissible. I skipped that part. And for genus G and with punctures V1, Vm, this TQFT functor associated to such decorated surface this vector space. Again, it uses Lubashenko's coent to the power G and tensor with decorated punctures, V1, Vm. They are objects in my category C. And you study home spaces to the tensor unit if you want to study coinvariance. Okay? And this TQFT that we defined via some universal construction, we also proved that mapping class group representations generated by this TQFT, they are equivalent to those defined by Lubashenko back to 94. So this is actually TQFT version or TQFT counterpart of model tensor categories. Or if you want, it's a generalization of Touraev's construction to non-semisimple model tensor categories. And in our recent theorem with Berger and Ingo, we proved that the following variant of the Verlinde formula, it expresses the structure constant in the proceeding ring in terms of values of modified trace of certain operators. So here, delta plus, delta minus, they are some non-zero scalars determined by the modular T action. And Fp of W is certain explicit endomorphism of projective generator G. And the SC of phi u, these are these Hopf links that we discussed previously. But I mean, these are quite explicit endomorphisms that one can compute in one or another example. And one just needs to calculate a modified trace of this endomorphism. And you calculate NUVW. So what's the idea of the proof? That NUVW is the dimension of home space from projective cover of W to U tensor V, right? And from TQFT side, I know that this home space from PW to U tensor V, it's an image of my TQFT functor of the decorated surface, which is two spheres with three punctures colored by PW, U star, and V star, right? But to calculate dimension of TQFT space for every surface Gn, I just need to calculate TQFT of three cobordism, which is sigma Gn cross S1. And this is a closed three-manifold. And so to calculate dimension of certain TQFT space, I need just to calculate invariant of this three-manifold. And one can use topological methods, so-called surge representation, to explicitly calculate the three-manifold invariant in the case of sigma 03 cross S1, which is equal to NUVW. And this is what we did, and we get this expression for fusion rules. And I think I'll stop here. Thank you.
Is there any questions? What about online?
Maybe I have a question. Somewhere in the middle, you described just after the modified traces that there was some module you could construct, and they reduced to traces on. Yeah, I think it was there.
So,
Trace on ordinary traces on some module.
right. Because you see, this phi m I defined this was special, called internal characters. They were this element that's the most radical one. They send the projective object either to 0 or the head to the socle.
So there's some.
Remember, David Rideout had these projective colors like diamonds, right?
Yeah.
For that diamonds, this phi m it sends top to the bottom. Or for whatever diagram you have, it will set always top to the bottom.
So
they're most radical, but they will send to trace what I wrote here.
M here is that socle.
M is from, so my category is ref V. M is VOA module, right? But I should define symmetric form on endomorphism algebra of G, project generator, right?
Yeah.
And home GM, it's a corresponding E module corresponding to VA module M, right? So that was say that. Phi M is sent to this standard symmetric form, the most easy one, just trace. Right? But there are, of course, many other central elements, elements of endomorphism identity that are sent to some non-trivial symmetric forms, which detect off-diagonal part of the action.
Yeah.
And they always appear on VOA side. When you, for example, if you consider S transformation of vacuum character, you will get these characters, but you will get also some symmetric forms which detect off-diagonal action. Yeah.
Okay. Thanks.
Any other question or comments? No? So if not, we thanks again the speaker. So we resume at 3:30 and there is a coffee break now.